Okay, good morning. Let's get started. So we were discussing unsteady diffusion, and we have also derived a general time stepping scheme, right? We derived a general time stepping scheme that is in terms of a factor called f, right? Can you help me write down this general time stepping scheme? This was AP phi p equals sigma A and B times f times phi and B plus 1 minus f times phi and B is 0, plus we have AP naught minus sigma 1 minus f times sigma A and B, is it right, times phi p 0 plus B, right, that is what we have, and the term B itself is f times SC plus f times SC 0 plus 1 minus f times 1 minus f times. So this was how much, f times SC plus 1 minus f times SC 0 plus SP 0 phi p naught. So essentially 1 minus f operates on both of them, right, on both of them or both of them, okay, times delta V, right, that is what we have, essentially goes to the other time level, that is 0, okay. And what about AP? AP was how much? AP naught minus f times SP times delta V plus f times sigma A and B, right, that is what we have, okay. So we have calculated all these things, and of course AP naught is rho delta V upon delta T, and all our A east, A west, all of them have their usual definitions, that is gamma east delta Y upon del X E, right, and so on, right. So we also said that we looked at two different schemes by setting the value of f. One was an explicit scheme, explicit time stepping scheme. This we obtained by setting a value of f equals 0, right, where the values of phi at time level t prevail over the entire time step, right, that is what we said. And also other properties that we looked at were the explicit scheme was only order delta t in terms of the truncation error, right, which we did not prove. We said this will be of order delta t, and is the scheme stable for any delta t that we choose? No, right, we kind of derived heuristically by looking at the coefficients of phi p naught, right, that if it is only kind of conditionally stable. So if we choose a delta t that is some factor times order delta x square, then only the scheme produces positive coefficients for phi p naught term, right. As a result, you would not get wiggles, and the solution you would get would be would converge, right. We also looked at another time stepping scheme by setting f equals 1, that was the implicit time stepping scheme, by in which we set f equals 1, right. In this case the values of phi at t plus delta t are assumed to prevail over the entire delta t, right. Essentially the unknown values are assumed to prevail, and then we also said without proof that this is also only order delta t accurate in terms of temporal accuracy. But what about the stability? Can we choose any delta t that we wish? We can actually choose any delta t, right. So this is any delta t can be chosen because this is unconditionally stable, that is what we said, we did not prove it again. So we only said this is unconditionally stable. From a heuristic perspective, we never got these coefficients which can become negative, right, we do not have those coefficients. So unconditionally stable. However, you cannot choose any delta t that you wish, because your accuracy may suffer, right, essentially as long as, so you can take as large delta t as possible, provided your accuracy is guaranteed, right, provided accuracy is guaranteed. Okay. So, if accuracy is not there, then you would have to kind of reduce the size of delta t, right. Okay. Fine. Now, we are going to see one more scheme. So, essentially the idea is these two time stepping schemes are only order delta t. So, as you refine the time step, your solution accuracy would only improve by one order, right. It is not going to be square. So, as a result, these are not very promising schemes if you want to reduce the temporal error. So, we are going to see something known as a Crank-Nicolson scheme, which is kind of intermediate between these two, okay, in which you would set f equals 1/2, okay, f equals 0.5 into the general time stepping scheme, and that would give you the Crank-Nicolson scheme. Okay. And now, let us kind of substitute these back into the original equation. So, into the general time stepping equation, that is this one, and then see what would be the corresponding equations. Okay. So, maybe you can substitute and again tell me what would these be. So, this would be A p phi p equals what would be the values on the right hand side. You would get a half here and a half from the first two terms, right. You have f times phi and b and 1 minus f, both of them will be half, right. So, that would be yeah. So, that is essentially 0.5 times sigma a and b times what? Phi and b plus phi and b 0, right. Is that correct? Okay. So, that is what we have. And then plus what else we have? Plus what about the A p 0 term? That would be A p naught minus 0.5 times sigma A and b times phi p 0 plus some b, right. Now, this b is of course, you have the source terms in there, which is basically this term, right. So, you have a 0.5 coming from S c, and S c naught and S p 0 phi p 0 would also have a 1/2 multiplying them, right. Essentially, you have 1/2 multiplying this entire thing. So, this is what? This will be 1/2 times S c plus S c 0 plus S p 0 phi p 0 times delta v. Is that correct? Yeah. Okay. So, that is the value. What about A p? A p was will be how much now? Same. A p would be A p naught minus 1/2 times S p delta v. Oh, sorry, this is minus S p, right. This is correct. Minus 0.5 S p delta v, and then plus 0.5 times summation A and b, right. Okay. Is that correct? Just plug in f equals 1/2 into the general equation. Okay. So, this is correct. So, these are the discretized equations for Crank-Nicolson scheme, and of course, your A p naught would remain the same, that is rho times delta v by delta t. Okay. So, what we say is that this scheme uses a linear interpolation between values of phi at t and t plus delta t. As a result, you would get this 1/2 factor in there. Okay. And so, what about the, if we kind of make some comments about this scheme, what do you observe here? Is the right hand side completely in terms of known values, or is it completely in terms of unknowns, or what is it? It is both. So, do you need to solve a system of linear equations at every delta t? Yes, you need to. So, this is more like a implicit scheme, but then you have half of the explicit component also coming into play, that would go to the b term, right. That is also there. So, if we look at the comment, so then this is so need to solve a system of linear algebraic equations at every delta t. Okay. Now, what about the coefficients? Would all of them be positive or would some of them may become negative? So, A and B's are always positive, right? A and B's are always positive. What about the coefficient for A phi p naught? Can this become negative? No? Phi p naught, can the coefficient become negative under certain conditions? It can become, right, because A p naught, if it falls below half of sigma A and B, this coefficient can become negative. This is similar to what we saw in the explicit case, right. So if your A p naught falls below 1/2 sigma A and B, then the coefficient of phi p naught could become negative. Okay, which is not good, because if it becomes negative, then you get into this oscillatory solution, which would eventually lead to divergence, right, because phi p naught is the previous time level value, and an increase in the previous time level value would actually decrease the value at the current time step for the same cell, and this is not good. This is again from a heuristic perspective. Okay, now this is rather kind of conflicting, right. We kind of have a value of f equal to half. So, we are saying we are solving a system of linear equations, but then we have now a condition on the stability, right. So, this is not like the implicit fully implicit scheme, right. This is kind of a half implicit half explicit. Okay. This is could become negative, which is not desirable. Okay, then you may have a question, then why do we actually solve for this scheme, right. It is not offering any advantage, you still have to solve for a system of linear equations. It turns out, without proof, again I am saying here, which we will do it later, or you would do it later, which would be the order of accuracy for time would for this scheme comes out to be order delta t square. Okay. So, this is second order accurate in time, which the previous two schemes were not, okay, because the previous schemes are only first order accurate in time. So, second order accurate in time. Okay. That means, if we can choose the delta t wisely, then we can make the error go down quickly compared to the other schemes, right. So, okay, so that is the advantage here. The truncation error you would make would go down at the rate of delta t square. As a result, you would prefer this as you refine delta t. Okay. So, that is the advantage that Crank-Nicolson offers on top of the other two methods, the explicit and the fully implicit methods. Now, if you go back to the equation, we had this condition, right. Now, we said, okay, there is this condition, this has to be satisfied, so that the coefficient does not become negative. Now, under what circumstances can we get rid of this coefficient? Only for fully implicit. Let us say you come up with your own scheme, you say, okay, f is why it should be 0.5, I would come up with my own scheme, I will say f equals 0.3, right. That is of course possible, it is not, people won't work with that as such, but in that case also, would you still expect a coefficient here or no? Yes, right. Essentially, for all the values of f that is other than 1, you would have a conditional stability only, like the explicit scheme. Okay. So, that is one thing to note. So, any f not equals 1 will have conditional stability, right. Okay. We will have only conditional stability, that is what we look at it from here. Fine. So, this makes a linear approximation between the two time level values. So, Crank-Nicolson makes linear approximation between t and t plus delta t. Okay. Questions till now? Now, how difficult or easy this is to code? So, if you have a fully implicit solver, is it very straightforward to do this thing? Right? It is, isn't it? Because you just have to take half of that amount and then put the other half into the b terms and so on, right? Whereas, if you have an explicit thing, you cannot do it easily. You still have to solve for the linear system. Okay? So, in terms of the implementation, Crank-Nicolson would be pretty much the same as what we have, right, for the implicit scheme. So, you do not have to code something extra once you have an code for implicit schemes. Okay. Questions? No? Clear? Understood? Fine? All right. Then let us move on. So, the next thing we are going to look at is we will evaluate the truncation error that we have encountered in our or made in our schemes. Okay. So, that is basically the spatial and the temporal truncation error analysis, because up till now we said we have made several profile assumptions everywhere, right, without actually looking at what is the order of accuracy of the finite volume scheme that we have developed. Okay. So, now we kind of revisit that. So, we will look at the truncation error that is made. So, essentially we made several profile assumptions. So, we will kind of quantify the truncation error. Okay. For both steady diffusion equation, which will give us the spatial truncation error, and we will look at the transient or the unsteady diffusion equation, which would give us both the spatial and temporal truncation errors. Okay. Fine. So, let us look at the steady diffusion equation. That means, we are looking at the spatial truncation error that we have incurred while making certain profile assumptions in the discretization. Okay. So, if you look at the steady diffusion equation, that is del dot gamma grad phi plus S phi equals 0, right. So, what are the several assumptions we have made in discretizing this equation using finite volume method? If you go back, source term linearization, okay, that is one thing, but source term linearization is something that we have already defended. So, before that, what was it? So, we had to linearize the source, but we assumed that the source term value is representative, the mean value in the cell is representative by the cell centered value, right, it is a representative of the mean value. So, that is the first approximation we have made, right. Of course, we have linearized the term as well, right, but before that we have done the representation by a cell centroid value, right. So, that is the source term, that is if you have integral S phi dV, we said this is represented using some S phi bar times delta V, right. So, that means the mean value of source term. Now, what is the mean value? An average value, that is average value over the entire cell, right. So, that is represented by the left hand side, right. If I have a mean value, that is represented by the left hand side, and the right hand side says that this is the average value is evaluated using at the cell centroid, that is S phi bar, this is at P, right. If we have cell centroid P, this is S phi bar P, right, that is we are calculating at phi P x P bar, right. This is evaluated phi P x P bar, right, like similar to what you have done in the assignment. So, the mean value of a source term is represented using the cell centroid value, right. That is, we calculate it at xp, right, that is what we have done. And after this anyway we have introduced a linear model, right, which we saw that there is no effect of it in at the time of convergence, because the linear model recovers the original source term that we have, right, at the as we converge our iterations. Fine. What are the other assumptions we have made? In the same discretization, phase centroid value. So, we got this other term which is basically del dot gamma grad phi. We did a Gauss divergence theorem, and then in the integration we have replaced it with a summation saying that the value of gamma grad phi on the phase could be represented using the phase centroid value. Okay. So, there is an analogy between what we are saying now for the diffusion flux on the phase and the source term that we have just said now, right. There is an analogy because we are talking about either phase centroid or cell centroid, right. So, that means the gamma grad phi on the phase E is taken to be the value at the phase centroid, right. So, the phase centroid value, if we can calculate, that remains the same on the entire phase, that is an average mean value, which we have taken and integrated converted our integral into a summation, right, because we had this integral gamma grad phi dot dA bar that we converted into sigma gamma grad phi dot A bar, right, that is what we have done. So, this is a phase centroid value. What are the other things that we have done? Have you done any other assumptions, profile assumptions? Linear profile assumption d phi dx. So, that means after this we have done the d phi dx and d phi dy, all those things. We said that this is a evaluated using phi east minus phi p upon delta x e. So, this is a linear profile assumption. So, we assume that the phi varies linearly with respect to x, right. So, these are the three profile assumptions we have made about the variation of the dependent quantities, right. All right. Then if you look at it, if we want to categorize these three, what about the first and two items that we have listed here? Are they one and the same? It is basically saying that if you have a value on a particular phase or on a particular cell that we are representing using the phase centroid value or the cell centroid value, right. That means the mean value is an approximation by the cell centroid value, right. That is what we are saying. So, essentially 1 and 2 are one and the same, right, they are the same, and the third one is a profile assumption, right, that is about calculating the gradient of the dependent variable phi. Okay. So, we are first going to look at the first one, that is basically this is the mean value approximation or average value in the cell, and then we are going to look at the second one. This is basically your gradient approximation, okay, and see what are the truncation errors that we would get from these two terms. Okay. Okay, in order to do the analysis, I would assume a 1D uniform grid. Okay, we will talk about a non-uniform grid little later. Okay, I will make you comment on it. So, that means first let us look at the mean value approximation. So, I am considering a one dimensional uniform grid. Okay. That would be what? That would look like this. Okay. So, we have a P cell east and west, and we have the faces, that is the little e and little w. Okay. I will also consider the dependent variable to be some function phi of x. Okay, it varies with x, and this is the P cell is the control volume we are looking at. Okay. Now, because this is uniform, this distance is, let us call it as delta x, and the distance between the cell centroids also would be delta x, right. It is a uniform mesh everywhere. Now, let me express phi of x about the cell centroid value, that is p, okay, about phi p. So, I want to use a Taylor series and expand phi of x, okay, that is within the control volume, okay, or between the control volumes, expand phi of x about phi at p, right. Now, phi at p is a particular value, right, and phi of x is a continuous function, right. Similarly, all the derivatives at cell p would be particular values, right. If you were to write partial phi partial x at p, this should be a particular value, right. Okay. Now, if I were to write this, how do I write phi of x? That would be phi p, okay, plus at any location, let us say x, that would be delta x, that would be x minus x p, right. If it is going to the positive x side, you would have positive delta x. If you are going to the negative x side, you will have minus automatically taken care of, okay, times what? Partial phi partial x evaluated at p plus x minus x p whole square by 2 factorial partial square phi by partial x square evaluated at p, and so on, right. That is our Taylor series expansion for variable phi of x about phi p, about the cell centered value. Okay. All right. So, now let me integrate this on the entire control volume. The idea is essentially we want to calculate a mean value for this phi of x, right. Now, phi of x could be something like a source term, right, it could be an s of x. Okay. Now, what would be the integration for the entire cell? We are going from west face to the east face, right. So, integrating the above equation over a control volume. Okay. That means, what would be our x extents? Integral x west to x east phi of x dx, right, equals, on the right hand side integration would be x west to x east phi p dx plus x west to x east x minus x p partial phi partial x p dx plus what else, integral x west to x east x minus x p square by 2 factorial partial square phi by partial x square p dx, and so on, right. That is what we have, right. We have just integrated the Taylor series about the control volume. Okay. All right. So, then let us leave the left hand side as it is and consider each and every term on the right hand side. Okay. So, what will be the first term on the right hand side? Integral x west to x east phi p dx. What will this be? Phi p times x, x is nothing but x east minus x west, that is phi p times delta x, right. Phi p is constant. So, phi p times x is what you would get, and substitute the limits, that is x east minus x west. X east minus x west is 2 delta x, is it? Why? This is x east is here, x west is here, is only delta x, right. It is not the capital E, it is only the little e, right. We are the control volume goes from x little west to x little east, right, not from x capital W to x capital east, right. Okay. So, this is only delta x, right. Yeah. Okay. What about the second term? Integral x west to x east x minus x p partial phi partial x p times dx. What will be this? Can you have a change of variables here? You call maybe some t as x minus x p, okay, let us have a change of variable, let us call t as x minus xp, then dt would be equal to dx. What will this be then? Integral partial phi partial x is anyway constant, right, times t dt. What will be the limits? xw minus xp, or so essentially if you have x west, then t would be, t west would be how much? xw minus xp, that will be how much? Minus delta x divided by 2, right, x west to xp. Okay. Similarly, xv east would produce t east, that will be x east minus x capital P, that will be plus delta x by 2, right. We are changing the limits from x east to x west to about xp, you would get half on each side, minus delta x by 2 to plus delta x by 2, right, because now your xp is 0. Okay. Very good. So, what is this value now? What will be this entire integral? Partial phi partial xp times t square by 2, right, going from minus delta x by 2 to plus delta x by 2. What will this be? This will be 0, isn't it? Just have an even function going from minus 0. This will be 0. Okay. This will be 0. Fine. What about the next term, that is x west to x east, x minus xp square by 2 factorial partial csvy partial x square at p dx. If you do the same analysis, right, what will that be? That will be minus delta x by 2 to plus delta x by 2. You will have partial square phi by partial x square times t square by 2 dt, right. Would it be this one? Yeah, just change of variables. Okay. Fine. Okay. Now, this will be how much? This will be partial square phi by partial x square evaluated at the cell center P times, this will be t cube by 3, that will be t cube by 6. So, this will be t cube by 6 going from minus delta x by 2 to plus delta x by 2. So, how much would this be? Sorry, this will be delta x by 2 to the cube, you will get 2 cube 8 48, right, in the denominator, and you have 2 1/48 terms. So, that will be 1 upon 24, right. So, this will be delta x cube by 24, right, that is what you would get. Fine. Now, let us go back and put it back into our equation. So, if you plug it in back, what will be the complete equation? You have x west to x east, phi of x dx equals, what is the first term? Phi p times delta x, right, that is the first term. What about the second term? 0. Third term, what we just got, right, this is order delta x cube term, right, that is what we got. All right, that is kind of sufficient to give us an idea. Now, how do I define a mean value of some quantity? That is nothing but integration of the quantity over the cell divided by volume of the cell or length of the cell or area of the cell. That means, I would divide everything by delta x. So, essentially divide by delta x, I would get integral x west to x east phi of x dx upon delta x. So, this is what? This is the definition for mean value, right. This is mean value, and what did we say? This is equal to now on the right hand side is phi p plus order delta x square, right. Okay. So, what did we say? We said phi p, right, is the value of the cell centroid, right. So, in our analysis, what did we say? We represented the mean value using only this quantity, right. So, what is the truncation error involved in that? Second order, right, it is a second order scheme. So, what we have is a second order accurate scheme, okay, when you represent the mean value by either a phase centroid or by cell centroid. Okay. right. Now, would the same thing apply for the gamma grad phi east also? Yes, because there also you have an integration on the face, right, and then you have gamma grad phi. So, it will apply. So, for both items 1 and 2 we have second order accuracy. All right. If it is kind of good to write to this coefficient. So, what we have is partial square phi by partial x square p. Okay. Now, let us say you have a source term. We are talking about represent the integration of the source term using a cell centroid value, right, average value. So, this phi is more like a source term, okay, or it could be gamma grad phi, something like that. Now, if you have a source term that is constant, okay, what will be this expression boiled down to? If we have a constant source term, what will happen to this term partial square phi partial x square? 0, right? You have a constant source term. Then what will be the mean value approximation of phi p? That will be exact, right? So, essentially this approximation is exact if S is a constant, right. If S is constant, dou square phi by dou x square, this will be dou square S by dou x square, that would be 0. As a result, your mean value for the source term would be only the value at the cell centroid, that is exact, because you do not have any more terms surviving, right. Fine. We are talking about spatial dependency here. Do not get confused between phi p, do not get confused with the linearization. Okay, here I have used phi, but this could be either a source term or it could be gamma grad phi, some variable, right. Do you see that? Okay. What about if the source is S is linear function of x? If it is a linear function of x, you will have ds dx would be non-zero, right. If it is a linear function, this would be non-zero. But what about the higher derivatives of the source term? Zeros. And but do you have a linear term coming into play here? No. So, even if you have a linear variation for S in x, this approximation is exact. Okay. But if you start having a second order representation for your source terms, then this representation is not exact. Okay. For example, if you would recall, I think in one of the assignments you had a source term in the first assignment, source term was given as some 5x square, isn't it. So, there if you had used the cell centroid value, which is 5xp square, you would be making this truncation error, right. Rather, if you had done integration just like using analytical expressions, then you would actually probably getting an exact value. Okay. That would be the difference you would have made. Okay. But once you convert your solution, you will not see any difference, right. So, that you can cross check by redoing it with a different source term. Fine. Everybody understand here? Okay. So, this is expression is exact for both the constant as well as a linear variation of the source term, but it incurs order delta x square truncation error if you have anything higher variation than that. Okay. You will have first term, but the thing is your first term is not surviving in the truncation error analysis because of the integration here, right. It only depends on this mean value approximation, only depends on dou square phi by dou x square terms, right. The d phi dx terms got cancelled, right. Mm-hmm. Yeah, sure. So, see the question is if I have source term as a function of let us say is a linear function of x, right. So, what did we say? We said that we are representing the mean value using only the cell centroid value, right. Now, these expressions are one and the same, either if you have phi as a constant or phi as a linear function of x, because this expression does not contain any first derivatives, right. If there are first order derivatives here, then this would be not exact even for a linear function of s, right. That is what I mean to say. Other questions? No? Clear? Okay. Now, one question to you is what will happen if you have non-uniform mesh? We consider delta x. Will this still be second order accurate if I have a non-uniform mesh? So, for that we have to go back. So, even if I have a non-uniform, so where is my term going out? That is basically the second term, right. So, even if I have a non-uniform mesh, what will happen to my limits? Would they be equally on both sides of the centroid? They will be. For the cell they will be, but cell to cell the delta x would be different, right. See, this is integration of limits from x west to x east. So, x west and x east would be always equidistant from the centroid, right, but not the delta x of p would be different from delta x of east cell. So, in that sense, even if I have a non-uniform mesh, would I still get a 0 for the second term? Yes, I will, right, because if I have a non-uniform mesh, so if we have a non-uniform mesh, then how does the mesh look like? It will look like I have one cell here, another cell here, and something else here. Okay. So, this is my P cell, this is my E cell. So, that means my delta x would be different from east P, sorry, this would be west and delta x east, right. The cell widths of each of the cells are different, but the limits of integration would be minus delta x p by 2 to plus delta x p by 2, that is x west to x east, which will be equidistant within the cell about the centroid, right. As a result, your mean value approximation will still have a 0 for the first derivative, right, but this, so it will be still second order accurate even if you have a non-uniform mesh, the mean value approximation. Okay. So, the mean value approximation is second order accurate even for non-uniform meshes. Okay. Fine, everybody agrees or questions? Okay. All right. Then let us look at the other term, that is the gradient approximation, right, because this takes care of the source term and the gamma grad phi on the faces. We will look at the gradient approximation, that is d phi dx equals phi east minus phi p by delta x e. That is the only term remaining, right, in terms of approximation, linear profile assumption. Okay, that is basically the gradient approximation. Okay, wherein we said partial phi partial x on east face is phi capital E minus phi capital P upon del x E. Okay. Now, let us consider a uniform grid again. Okay, it is basically same as what we had before. I am considering a uniform grid, and this is P, this is capital E, this is west, and our faces are east and west. Okay. Now, let me expand phi p and phi east about the face E. Okay. So, essentially we are expanding the values, expanding phi capital E and phi capital P about phi east. Okay. About the face value, I am expanding the cell values. I mean, essentially we are interested in what is d phi dx, right, at the face. So, when would I calculate d phi dx at the face? Only if I expand about that term, right. If I expand about phi p, I will get gradients at p. That is not what we want. What we want is d phi dx at face value E. So, we are expanding about east and p about the face, that is little e, so that we can see if we can get an estimate for this value, right, because this will show up in the Taylor series. That is what we are doing. So, then what would be the distances now? About phi little e, what will be these two distances? This will be delta x by 2, the other one would be distance wise delta x by 2, but it will be in the negative x direction. Okay. So, this is x direction. Okay, then what would be phi capital E about phi little e? Phi little e plus x east x capital E minus x little e, that would be delta x by 2, right, partial phi partial x at E, is that correct? Yes, okay, plus what else? Delta x by 2 whole square upon 2 factorial partial square phi by partial x square at east and so on, right. What about phi p, about phi little east? Phi east minus delta x by 2 partial phi partial x about east, what next? Plus delta x square upon 8, right, 8 partial square phi by partial x square about east minus and so on, right, correct. Okay. Then what do we want? We want phi east minus phi p. Let us subtract 1, subtract 2 from 1. So, essentially we are looking at 1 minus 2. So, on the left hand side we have phi east minus phi p equals, what will be there on the right hand side? Phi little east gets cancelled, first term gets cancelled, second term gives rise to 2 halves will be 1. So, this will be delta x times partial phi partial x at east. What about the third term? Gets cancelled. What about the fourth term? You will have some value that will be order delta x cube or 4 or 3, okay, cube times partial cube phi by partial x cube at E, right, that is what we will have. Okay. Then what is that we want? We want phi east minus phi p by delta x equals partial phi partial x at east plus what will be this term? Order delta x square times something, right. So, when we calculate partial phi partial x, if we only approximate it with phi east minus phi p by delta x, what will be the truncation error that is involved? Order delta x square, right. So, this is also second order accurate. Okay. So, essentially the linear profile assumption for the gradients partial phi partial x E is second order accurate, right. Okay. This is second order, that is order delta x square. So, with this all the terms that we have or all the profile assumptions are now done, right, and all of them are what order of accuracy? Second order. As a result, the steady diffusion equation is order delta x square, okay, for I would say uniform meshes right now, because that is what we have considered, okay, for uniform meshes. For uniform meshes, okay. We have also seen that for non-uniform meshes the mean value approximation is still second order accurate. Okay. This is order delta x square because every term has truncation error of order delta x square in the steady diffusion equation. Now, what about non-uniform mesh in the context of gradient approximation? So, this is a non-uniform mesh for gradient calculation. Is it still second order? Yes? Yes or no? No, why? Delta x will be different, right, because what will happen to this delta x by 2? This will be delta x E upon 2. What will happen to this guy? Delta x p upon 2. As a result, these two, as a result, this would not get subtracted off, right. So, sorry, yeah, I mean the second term, right, this term would not get subtracted off. So, this will still remain there. Okay. So, essentially this term would still remain there. This is delta x E by 2 whole square, and this would be delta x p by 2 whole square, right. As a result, you would not get order delta x square terms, rather you would start getting terms which are order delta x. Okay. That means you would still get, it will be only order delta x, this will be only first order accurate if you have non-uniform meshes. Okay. As a result, the if you have non-uniform meshes, the total order of accuracy will come down to first order, because some terms are first order accurate. Okay. So we have to now look at the unsteady diffusion equation, and in the unsteady diffusion equation we will look at both spatial and temporal truncation errors, but the spatial errors are pretty much the same as what are there in the steady diffusion equation, because those are the same assumption we have made. But anyway, we will quickly look at that, okay, in the next class. Fine. So I am going to stop here. We'll see you guys in the next class. Thank you.